Alright, hi everyone, welcome to my YouTube channel, City of Electrons. So, before I mention what we are going to talk about today, let's just start with this and then we'll flow into it. Okay, now when you see these, what comes to your mind? Smartphone, mobile phone. Okay, now what happens with this is that we use it for different tasks. You want to make a phone call, you want to reach out to someone, you want to maybe calculate something, or you want to browse the internet. Tasks, like to accomplish different tasks, to do things, we make use of the mobile phone. Okay, now the thing is this: when you interacting with the mobile phone, you need to do something. Okay, maybe you take an action, you touch somewhere in the on the screen, you say something like voice recording, you do something. Consider that as input. Okay, consider that as input. Then the mobile phone receives what you do, what you give as input, and then it works with that and then it gives you output. Okay, which is usually displayed on your screen or from the speaker. If it's an audio output, you get it from the speaker. If it's a visual output, you get it from your screen. So the thing is this: you give the phone something, you want to do something, and then the phone gives you output. But between, ladies and gentlemen, between the input and output, okay, how is your mobile phone able to receive your inputs? That's one thing. Then processing that your inputs, then giving you outputs. Okay, note that what I just explained, input, process, output, okay, what I just explained is for electronic devices, not just your mobile phone, your computer, and sensors even. Okay, sensors, some embedded systems also. But in this video, we just try to keep our example within mobile phones and computers, laptop or desktop, whichever one, just for simplicity. Now, input, process, let me write this here: process or processing. So input, processing, and then output. Now, for further simplicity, in this video we'll talk about the processing. How is your input processed, or what is responsible for processing your input and then giving you output? Note that when you open, maybe if there's something wrong with your phone and then you take it to someone who is going to fix it, when they open up your phone, okay, you usually see a green board, kind of, and on it you have different components. Okay, yes, say you have capacitors, resistors, different components on it. Okay, different components. Okay, inside this mobile phone, I think what I drew is too large, but no problem. You understand the point. When you open the mobile phone or your computer, you usually see a green board, mostly referred to as motherboard or printed circuit board. On it, there are different components. There are different components: capacitors, resistors, and transistors. Then there is a particular component. Let me do that properly. There is a particular component inside of it. Okay, all the other components inside, they serve as what this main component uses to process information. That is, these other guys will serve as something that will receive will help to receive input and give out output. However, the processing happens in this. Just like the human body, we have hands, legs, and everything, okay, which executes action. But the thing is that the processing of the human body processing of input and output in the human body happens in the brain. Okay, happens in the brain. When the brain receives, oh boy, when the body receives an input, maybe somebody, you have a physical touch, on your hand or any part of your body, that sends signal to where? The brain. That sends signal to where? The brain. So call this guy brain. Let's put this here, brain. So signal is sent to the brain. The brain will process it and send back, send output signal. Maybe you just rest your body on a sharp object, maybe on the wall, and then signal will be sent to your brain that there is something input. The input signal, there's a sharp object there. Then the brain will process it and say, okay, for you to live there, you have to maybe take your body out. Your brain sends signal to that particular part of your body so that you can withdraw yourself to protect you. So inputs from the devices to the brain process and give output, and the device helps implement that output to other devices. So there is a main device inside this board, main device, and it's called what? What do you think, guys? What do you think? I know most person will say CPU, which is correct. Central processing unit, which is correct. Okay, but what we'll focus on in this video is that something that functions as a central processing unit. Central, simple word now, central, that's the center. Okay, processing, center for processing, and it's a unit, central processing unit. Okay, so what that unit that functions as a central processing unit is known as what? Microprocessor. Okay, now it's also referred to as, so let me just put this here, it's also referred to as hearts of the computer, microprocessor. Okay, so brain or heart, whichever one. But when we say heart, if you take out your heart, the person is dead. If whoever takes out his heart, like literally, that person is dead. So without the heart, there's no function. Without the brain, yeah, that kind of thing. So microprocessor, this is what we are talking about today. Microprocessor. Okay, so I believe with this little drama here, we'll have a good overview of what the microprocessor is. It is that component or unit that functions as a CPU. What happens with the CPU? It is where all your processing happens. You receive input, it's being processed, the output is given. Okay, so you get the gist. Keyboard takes in input. Let's say, for example, keyboard takes in input, processed in the processor, then output goes maybe displayed on your screen, that's your monitor or your speaker. Simple. So microprocessor, are we getting it? Now I just have to write all this out to make things easy so you can just see and read and that kind of thing. So what we are going to cover in this video, which we have started already, we are going to cover the definition of a microprocessor, components of a microprocessor, evolution of microprocessor, types of microprocessor, and application of microprocessor. Okay, so for definition, I think we've done that already, that a microprocessor is a unit that performs the function of a central processing unit, and I've explained what happens with that central processing unit even with an example, so you can just take the video back and watch again and again. Alright, then components of microprocessor, very important. Since we know that a microprocessor exists, I'll come back to this a lot. So what are the components of a microprocessor? That is, what is a microprocessor made of? It's made up of three main components. Alu, please, CU, and then registers. I think I should have used a different color for this. Register or registers. So for this guy, ALU means arithmetic and logic unit. Okay, this component inside the microprocessor, this is where all the arithmetic, mathematical computation is carried out. Originally, like in those days, the early days of microprocessor, these guys were produced for mathematical computation. Okay, so arithmetic, mathematics, addition, subtraction, multiplication, division, okay, all those operations. These components, or this U for units, this unit inside the microprocessor is responsible for arithmetic operation. Logic, which is and, or, nor, not, all those your logical gates. I'm not going to logic in this video, okay? I'm just telling you what is contained in the microprocessor. So your arithmetic and logic gates, logic operations, all those are handled in this unit. Then for this, CU, again, U for units. Boy, what's happening? Yeah, U for unit, C for control, control unit. This unit is in charge of data flow, not just data flow, but in charge of operations, controlling the operations. Okay, arithmetic and logic unit, do this now, do addition, do this. Like, this is a control center. Okay, it's a control, let me just say control center, in charge of the flow and operations. Registers, these are storage, let me say elements or storage device. Let me just use that word, storage. Okay, they're mostly temporal storage. Okay, so these are the three main components in the microprocessor. Okay, and we have them here: arithmetic and logic units, control units, and then registers. Okay, now the next thing we'll talk about is evolution of microprocessor. When we say evolution of microprocessor, we mean how it has changed over the years, how it has evolved over the years. Okay, now I could have just written this in as first generation, all right, second generation, right, but let's just put this in tabular form to make this easy. So you can see here we have the generation, that's first generation, second and third, and so on. Size, speed, instruction, number of transistors, year, and name. Now, why do we have this column? Of course, generation, we just know that the first generation of microprocessor, the second generation of microprocessor, and so on. That's clear. When we say size, what do we mean? What do we mean? Now, I will pause here. I will stop in this column and explain the basis of the evolution. What is the evolution of microprocessor based on? This is the kind of the most important column here. Okay, so the evolution of microprocessors from the first generation till date can be categorized according to the size of the microprocessor, which has to do with what? Bits. Okay, now you can see when we say size here, inside the column, what do we have? 4 bits, 8 bits. Bit is what we see. Now, what is a bit? And how does this really relate to size? How can you say a bit means size? Then the microprocessor is changing by a bit, and you say that's changing by size each generation. How? Let's go. Now, the first thing to note, let me give space for this. Take these guys away. We'll need them later, so let me just take it aside. That's okay. Now, first thing to understand, when we say bits, what do we mean? We mean there are two possible states. A bit is 1 or 0. These together makes 1 bit. It's funny how this is the sign. Remember this 1 0 1 0. This is 1 bit. Okay, this is 1 bit. Now let's take that out. Are we together? That's 1 bit. And the thing is this: registers, look at this. Registers are made up of what? Flip-flops. Flip-flops are made up of what? Transistors. We are still on the bit matter, we are still on the bit matter, made up of transistors. Now, when transistor allows current to pass through a point, consider that as 1. If a transistor do not allow current to pass through a point, we consider that as what? 0. The building of a transistor, how it looks like, we will not go into that, but just know, bear in mind that transistor has 3 pins: base, emitter, collector. That's for BJT. And when you apply certain voltage to the base pin, usually 5 volts, okay, it allows current to flow through, and we'll consider that as what? High, which is same thing as on, or you say 1. Then if the voltage applied is 0 volts, which means no current to the base pin, or voltage rather, or current in BJT, okay. Yeah, if we do not have up to 5 volts, maybe like 0 volts, which means no current going through the base pin, we consider it as what? Low, which is the same thing as off, and it's the same thing as what? 0. Same thing as 0. Okay, so a transistor will give us either a 1 or a 0, and these guys are made up of transistors. Flip-flops are made up of transistors. So just take this idea of 1 and 0, put it in flip-flop, copy, paste, put it in flip-flops. So meaning one flip-flop, this is one flip-flop, guys. One flip-flop can be either what? A 1 or a 0. Are you seeing it? This is what? 1 bit. This is 1 bit, one flip-flop. Okay? Now, registers are made up of what? Flip-flop. We said that just now. Registers are made up of flip-flop. So if we have 4 flip-flop, it means we have what? Remember I said this is what? This is what? 1 bit. I said that just now. Because a bit is 2 possible states, 1 or 0. Okay? Now, since 1 flip-flop is giving us 1 bit, that means 4 flip-flop is giving us how many bits, guys? It's giving us how many bits? 4 bits. Are we together? Okay, so this simply means if we now increase the number of transistors, increasing the number of transistors simply means you are increasing the number of flip-flops. Okay, so increasing the number of flip-flop, which means you are increasing the number of bits. So if we now have 8 flip-flops, 8 flip-flop, that would be what? 8 bits. 8 bits. So are we seeing it now? 1 0, that's 1 bit. 4 bits will now be what? Let's see, 4 bits will now be 1 0 0 1. Yes, or it can be 1 1 1 1, or but 4. Remember, only these parts, only these parts. This one here can be 1 or 0. 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 Okay, are we seeing what's happening here? So this is just 1 bit. This is just 1 bit, which is what? 1 or 0. Okay, now this is what? 4 bits. I think I should have just written only one thing there. I think I should have written one thing here. Yeah, I should have written it like this. Still the same thing, I should have written it like this, 1. So this is 1 bit. Or we just put it like this, 0. This is also 1 bit. Are you seeing it? Now for this we have 1 2 3 4, which means we have 4 bits. So when you say you have 4 flip-flop, it means you have 4 bits. It means your processor can handle 4 bits of data at once. Okay, so if your processor has 4 bits, it means your processor can handle 4 bits of data. If your processor has 8 bits, it means your processor has 8 bits of data. When I say your processor has 8 bits, it means the register and its operation, they are made up of what? If for 8-bit register, it means it has 8 flip-flop and it can handle 8 bits of data. So it simply means 8-bit flip-flop, 8-bit register can handle more operations than 4-bit register. So this is what we mean by difference in size. So this guy has more size than this. Okay, I know I've said a lot just now, but please pause the video, take it back and go over this. You will get it. It's straightforward. I'm just trying to, if you listen well, you see I'm taking this thing again and again. I'm just repeating this stuff, trying to make it as plain as possible. Okay, please just try and follow, please. All right, now with that being said, you can see the difference in the generation of processors. The main difference is what? The size. Look at it. The evolution of microprocessors from the first generation till date can be categorized according to the size of the microprocessor. The size, which has to do with what? Bits, and that I have explained here just now. Okay, so looking at the microprocessor, which is made up of ALU, CU and registers, we can clearly see that over the years the change happens with the register, because we said the register is made up of what? Flip-flop, and then flip-flop made up of transistors. So as we increase the number of flip-flop, that is how we increase the size. Okay, of course there will be advancements in this and this, but the main thing to note in the advancement is the register, and that's the size. Okay, so in this table, where we really hold the change is these guys, the size. Of course, as you increase the size, we have higher speed here. Speed just means how fast your computer is. Okay, and then instructions per second. So how many instructions can your microprocessor achieve in 1 second? That's just the meaning. The number of transistors, of course, we already made mention of the fact that registers are made up of flip-flop are made up of transistors. We already mentioned that. So in the first generation, this 4 bits, how many transistors are inside of it? And this is just the year and then the name of the microprocessor at that year. Of course, there are many other details to this. This is just an approximate detail. Okay, what we have in this table is just an approximate detail. That's why I said here, note that the figures for numbers of transistors and instruction per second are approximate values. Okay, they are approximate values. And here there are still other companies here. There are still other names here, but this is just an approximate. This table is an approximate table. It contains approximate details. Okay, but approximate table, Jesus. All right. So note the following. Most of these notes I've said them, but just note. Size simply means the number of bits of data that can be processed at a time in one operation. I've explained that a lot. Okay, so when we say 4-bit microprocessor, we mean the processor can handle or process 4 bits of data in one operation. Remember I said that. Then when we say speed refers to the clock frequency of the microprocessor. That is, how many cycles can the CPU go or perform in 1 second. So 3 megahertz means 3 million cycles per second. Okay, so if we say, that's what we're talking about now, speed, it means how many complete cycle can your processor achieve from 1 point, like a complete, cycle now, a complete cycle of instruction, a complete cycle. How many cycles can your CPU perform in 1 second? Man, that's small. 1 second. And your CPU, if you say your CPU has a speed of 3 megahertz, it means your CPU can perform 3 million cycles, can go 3 million cycles in 1 second. That's fast. That is fast. You can check your phone. Go to your phone setting and you you know how fast your phone is. And then even your laptop, go to properties, you see how fast. I think mine is 2.5 megahertz, I think so. I'll check later. Okay, so note that a register is a storage which is made up of flip-flops. A 4-bit register is made up of 4 flip-flops. One flip-flop holds an amount of voltage which is considered high, which is on, that is 1, or the opposite, low, off, that is 0. You see, the properties is just like transistor. That's to tell you flip-flop are made up of transistors. Okay, so this is binary, which is 1 bit. 1 bit equals 2 possible states. It's either a 1 or a 0. Okay, so a flip-flop will contain either 1 or 0. Okay, at one time. Okay, now flip-flop are made up of transistors. That is, as we increase the number of transistors, we actually increase the number of flip-flops, which means increasing the registers, and that is a larger microprocessor in terms of data processing. This last thing is very important in terms of what? Data processing. So when we say larger microprocessor, we do not mean physically larger. We do not mean that the microprocessor will look very large when you look at it. No, that's not the meaning. It means larger processor in terms of how much data it can process. It can process 4-bit data, it can process 8, larger processor in terms of data processing. Good. I believe after watching this video you should get this thing, because I've repeated a lot of things. Yeah, I've repeated a lot of things. So types of microprocessor. There are 3 major types of microprocessor. Okay, I think we've gone far. Okay, so we've done definition, components, we've done evolution. Oh, I didn't talk much about these other parts. Okay, I didn't say much about this because you can always look up what you have here. These are just the name of the different generation. These are just the name, and these are just their years. Okay, you can even take a screenshot of this and look at it. But the most important thing to understand here is these guys. Okay, because this is what even led to the change. The change in different generations are based on these guys. So I just explained this. This is just generations. So you can always look up, oh, what are the instruction per second for the 3rd generation? Oh, you come here, look, oh, 2.5. Like I said, it's an approximate value. I already said it's an approximate value, so you can always browse this in later. Okay, so I'll leave this here. So the next thing we'll go to are the types of microprocessor. Types. Oh, all right. Types. Now, there are 3 major types. Okay, there are 3 major types: CISC, RISC, and special purpose microprocessor. Now, let me start with the 3rd one. It's very, very straightforward. Special purpose microprocessor are processors designed for special purpose. Full stop. Done. Okay. Examples of these guys are just microcontrollers like Arduino, Raspberry Pi, ESP32. If you don't know what all those things are, no problem. Don't worry about it. But just know that any microprocessor designed for a particular or special purpose, just know that that is a special purpose microprocessor. Okay, simple as that. That includes co-processors. Co-processors meaning a processor that works with the microprocessor. Example, microcontrollers, that is Arduino, Raspberry Pi, ESP, and things like that. So just leave that there. Special purpose microprocessor is a type of microprocessor. Then RISC and CISC. I feel I will take these 2 together because they are like opposites. They are like what? Opposites. For CISC, it means complex instruction set computer microprocessor. Okay. Now, complex is just like the name. Things with computer, they are just straightforward. They name the things after themselves. So it's just like the name. Complex. So it is designed to execute complex instruction. plain and simple. And when we say complex instruction, what do we mean? That is executing a combination of multiple single instructions. Look at this. Just look at this. If this is an instruction, this is another instruction, this is another instruction, and we have another instruction here. In CISC, which is complex instruction set computer, in that type of processor, it will take all these single instructions, it will combine them, combine the single instructions to execute. That combination is what makes it complex, because it now has what? Multiple single instructions. Are we seeing it now? So what are the features of CISC? What are the features? The following are features of CISC and CISC. What is the name? A. Instructions in CISC are complex. Very clear, because you are combining single instructions, so the instructions there are complex. The second thing is that it takes more than 4 cycles to complete an instruction. So after the processor goes 1 cycle, it's not completed. It will go another cycle, until 4 cycles at least. It can take more than 4 cycles. Note, it can take more than 4 cycles, but at least 4 cycles to complete an instruction. Then its code is short and thus requires less memory, of course, because we are combining 4 instructions together. So we are not writing a separate code for each instruction. We are combining at least 4 instructions together. Okay? You can have more than 4, of course. We are combining different instructions together. So we are not writing code for each, like one complete program for one instruction or that one. No, we are combining them. So we have short code, all right, and thus we require less memory. Okay? Then, since we are writing short code, it means less emphasis is laid on the software. You know, a code gives you a software. So less code meaning short code meaning less emphasis on software, and then more emphasis on what? Hardware. Now come to RISC, is the opposite. These two things remain the same, instruction set computer, but this guy is the difference. This is what? Reduced. Okay, reduced. So it is designed to execute what? Reduce instruction. Very simple. So that is executing single instruction. So in this case, we are not combining them, we are doing individual. So you will execute this guy, execute this guy, execute this guy. Are we seeing it now? Reduce instruction set computer microprocessor. But the thing is this: while we execute single instructions in RISC, it utilizes the concept of pipelining to execute part of the instruction in parallel. Pipelining idea just means while you are executing an instruction, you are fetching the next instruction. This is the simplest way you can look at the word pipelining. Okay, of course you can leave comments in the comment section and tell me what you think about pipelining and other things, but as simple as I can get, or as I can think of it, is that while an instruction is being executed, the next instruction is being fetched at the same time. So the concept of pipelining now gives room for parallel operation. So in this case, or parallel execution, yeah. So it utilizes the concept of pipelining to execute parts of instructions in parallel. So the following are features of RISC. It's almost like, and the way we arrange it here is just like opposite, so it can be easy. Jesus. The way we arrange it here is like opposite, so that it can be easy for us to bear in mind. You see, for CISC, instructions are complex. RISC, instructions are simple. Good. CISC takes more than 4 cycles. RISC, it takes 1 machine cycle. Even if I don't click machine, it's the same thing. But I think I should leave it. then add it here. It takes more than 4 machine circles. Yeah, it takes more than 4 machine circles to complete. Oh boy. For CISC it takes more than 4. For RISC it takes 1, just 1. And even while that one is executing, it's fetching the next instruction based on pipelining concept. Then C, its code is lengthy. For this guy the code is short and requires less memory. For this guy its code is lengthy and therefore requires more memory. Lengthy code meaning more emphasis on software and less emphasis on hardware. I've explained this third one already. So this is just the overview of types of microprocessors. And then for applications, using communication system, using communication system, should I explain something like that just I use this is communication system now. I use our mobile phone to start this video, and of course that's using communication and so many things. Okay, and then of course medical devices, industrial control, control systems in industry, and Internet of Things, which is IoT, then our entertainment, and then defense system, etc. You can leave in the comment section how is the microprocessor used or applied in these different areas. You can leave that in the comment section. And then if you have question or anything, comment please. And then like, share, subscribe. And I hope this video helped in one way or the other. And we've done this thing, we've defined it, we mentioned the components, went through the evolution, the types, and then application. So we'll stop this here. Thanks a lot for watching, and bye for now. See you in the next video.